view full screen. You begin this effort with defining what the empirical formula is. I believe I mentioned it in the distant past when we first crossed the terminology of formulas. But empirical formula is the smallest whole number ratio of elements in a compound. If we have a compound given, for example, ethylene, I can divide the subscripts by 2 and have CH2 like this. The smallest whole number ratio is the empirical formula. This C2H4, of course, is the molecular formula. So the molecular formula now is the actual whole number ratio of elements in the compound. For problems that you will be working, you will need to know the relationship between empirical formula and molecular formula. And the difference is what we call a whole number multiple. Now, if I had the empirical formula times a whole number multiple, say n, I would have the molecular formula. For example, if we go back up here to the example we used here, I've got a CH2. So I put a CH2, say you're given the empirical. Well, to get to the molecular formula, C2H4 is pretty straightforward, just times 2, which would be the whole number multiple. Now, the essence of this part is that you can determine a whole number multiple for formula, given the empirical formula, because this is the empirical formula, and then you can calculate empirical weight, just like you did molecular weight. 12 plus 2, okay, 14. So the empirical formula weight, right there, times the whole number multiple, right there, is equal to the molecular weight. We'll work a problem here in a few minutes where you will be asked to determine the molecular formula based on given some data for empirical formula. You will determine the empirical formula, but the one thing you'll have to have in the problem is mole weight. You have to be given this. So in the problem, it'll give you, say the compound has a formula weight of 90 grams per mole, and then you use the other data to calculate the empirical formula, then the empirical weight, and then divide the empirical weight into the 90 or whatever, and find out what the whole number multiple, and see and then when you get that, you'll multiply it through the formula, and get the whole number, get the molecular. There's a very succinct procedure for going through this type of problem. Very straightforward. Data will come to you in one of two forms. It will give you the mass of compound and mass of one of elements. Or the data will come to you in percent per 100 weight. If it comes to you in the form of mass of compound and mass of one of the elements, you must convert this to percent per 100 weight. Okay, here you're given mass values, and I told you to convert to 100 weight. Okay, what do I mean? An oxide of osmium is given. Just put OS oxide. 2.89 grams. That's the compound weight. So that contains all the elements. Then you're given the mass of osmium. Okay, and then you're asked to determine the empirical formula. To get that empirical formula, you have to convert this to percent per 100 weight. Okay, it is calculated by part over total times 100. That'll give you percent per 100 weight. So if I took the 2.89, the compound weight, right, minus the osmium, what's left? Oxygen. So if I have the weight of oxygen in osmium oxide, that's equal to 2.89 minus 2.16 grams of oxygen in that problem. So what we got to do is calculate the percent of osmium is equal to 2.16 grams, and grams of course cancel out, 2.89 times 100%. And then the percent of oxygen is, well, you can do it with 0.73 over 2.89 or 100 minus the value we get for the. So this one gives us the 74.74%. That's the per 100 weight. Then I can, if that's per 100 weight, then I can get the oxy simply by subtracting 74.74% from 100%. Here, that's very, very important that I want you to notice. When you make this calculation right here from this data, what you're getting is per 100 weight of compound. Okay, so 74.74% of whatever weight you have is osmium. 25.26% of whatever mass you have in that compound is oxygen. You got it? Okay, I'll ask you a quick question. Now with that in mind, how do you get the empirical ratio? Does it say? Now what I write down right now, when I write the percentage symbol, it means percent per hundredweight. Got it? And the next one would be grams I get from that percentage hundredweight. So watch this. You go for percent. Once you have percent per hundredweight, you can get grams. Then divide by formula weight, you get moles. And when you get the moles, you set up a ratio, a mole ratio. Then you reduce ratio, and that gives you the empirical ratio. Okay? You were given this, or you determined this from the data you were given by doing the percent ratios. Everybody okay on that? Set this up as the component. There's osmium and oxide, colon, osmium percentage per hundredweight, oxy percentage per hundredweight. Draw a little if-then issue and just drop the percentage and put grams. Drop the percentage on oxygen, grams. Because you're working in grams per hundredweight. And we just determined that, you told me, that if I had 100 grams osmium oxide, that's the grams I'm going to have in osmium and oxygen. Now that takes us from here, step 1, to step 2. Step 3 is calculate the moles. Divide by formula weight. Okay, so put these out here for you, right there. So I'm going to come down here and osmium, oxy, like that, and I've got 74.74 grams and 25.26 grams, and I'm going to divide by the formula weight, 190 grams per mole, the osmium, and I'm going to divide the oxygen by 16 grams per mole, right there. I'm going to have the metal first, followed by the non-metal. So I'm going to set up osmium to oxide, like that. What I'm going to do is osmium equals, colon. So when I've set up the ratio, I'm going to do this, which is, you recognize ratio, but I'm going to put a blank and blank. And the numbers that I've calculated up here, as for moles, I'm going to put on the top. 0.3934, that's for the osmium, and 1.5788 for the oxygen. See what I did? I'll set up the ratio, and I draw a couple of lines of colon. If I had 3 elements in there, I'd put a colon in the third one. Okay? To get the reduced ratio, and then finally your empirical ratio, divide by the smallest of the two numbers, or the set of numbers. So the smallest is 0.3934, 0.3934, and this gives us a 1:4 ratio. This is the empirical ratio. Right there. So if that's the empirical ratio, then the empirical formula is then OSO4, right there, osmium oxide. Okay, you're given a malonic acid. Now malonic acid is a organic compound containing carbon, hydrogen, and oxygen. When working a problem like this, and you'll get it, just like I'm giving it to you now, you set up your elements in this columnar format right here. Then go into the problem and put out to the side over here the percentages. This one gives 34.6% by weight in carbon, 3.9% by weight of hydrogen, and 61.5% by weight of oxygen. Percent to grams to moles. Set up a ratio. Reduce the ratio. Then we get the empirical ratio. That's the pattern every time. Okay, so 34.6% is equal to, or gives, and can be translated into 34.6 grams, 3.9 grams, and 61.5 grams. Carbon, I'm going to put a slash right there, is 12. I know it's grams per mole. It's going to come out in moles anyway. What's the formula weight of hydrogen? 1. And what's the formula weight of oxygen? 16. So this gives us, for the carbon, 2.883 moles, 3.9 moles of hydrogen, 3.844 moles of oxygen. At this point, I kind of just put a little bracket right here, and I'll set up my ratio CHO. And I put, since I have 3 elements, I'm going to put 3 lines, just like that. And on the top, I will put the mole numbers. Carbon was 2.883, hydrogen 3.900, and 3.844 for the oxygen. And to get the empirical ratio, we divide this set by the smallest of the collection. Well, it looks like this one on the end here, 3.844 against 3.88. So that's no, I'm sorry. That's the smallest one. 2.883, 2.883, 2.883. Okay, look at what we got here. This gave us a 1.3, 1.3. Now, at this point, you round it to the nearest whole number. Now, there's a twist in calculating these. You might get a problem that will have A to B with a ratio of 1 to 1.25, or 1 to 1.50, or 1 to 1.75. Multiply these by whole numbers to get them to whole numbers. In this, if you get these, you have the legal right in the problem to multiply them by these whole numbers. And I'll check it before I give it to you on the exam. I'll make sure if something like this pops up, I make sure it doesn't come up in a fraction like this. Now you have to interpret that as a 2.5, rounded to 3, and so what you would do is go 4 times 1 to 3. I mean 1.25, 1.25. 1 to 1.3 to 1.3, and say that is. That's why I didn't want to use this one. 1 to 1.25, 1.25. So this one would be a times 4. And so you'd have 4 to 5 to 5. There's your empirical ratio. CHO 4, 5, and 5. And there's your empirical formula. Acrylic acid, carbon's 50% by weight, hydrogen 5.06 by weight, oxygen 44.4 by weight. And if we follow the procedure, percent to grams to moles ratio, reduce, and then we get the empirical formula, like that. So this would go to 50.00 grams, 5.60 grams, and 44.4 grams. Divide this one by 12, 1, and 16, and we'll get the, so we get 4.167 mole of carbon, 5.6 moles of hydrogen, 2.775, and then we set up our ratio, 1, 2, 3, since we have 3 elements in the formula, 4.167, 5.600, 2.775. Smallest number is 2.775, 2.775, so 5. And then you get your empirical ratio. What do I have to do to this one? This is exactly the way it came out. So if I have a 1.5 here, all I have to do is double this, and then I get the final empirical ratio, 3, 4, 2, right there. And then your empirical formula is CHO 3, 4, and 2. Okay, the first thing you need to keep in mind is there's a relationship between molecular formula and empirical formula. The problems you will have on the test will ask you to calculate a molecular formula, but you'll give you data for getting the empirical formula. Once you get the empirical formula, and you'll have this given, they have to give you the mole weight of the compound. Otherwise, you can't calculate that whole number mole. So here we have 26.7 grams, 2.2 grams, same procedure, 1 gram, and we divide by 12, and then 1 and 16 to get the mass values in the moles. So the moles of carbon is 2.225, hydrogen 2.200, and 4.443 for oxygen. And we set up our 3-element ratio to get our empirical ratio. So for carbon, 2.225, 2.200 for hydrogen, and 4.443 for oxygen. And looks like the smallest number is 2.200. Well, this gives us a reduced ratio of 1 to 1 to 2. So the empirical formula is CHO2. And from this, we can get the empirical formula weight to equal carbon plus hydrogen plus 2 oxygens, 12 plus 1 plus 2 times 16. And you can use AMUs if you wish. So the empirical weight is 45 atomic mass units. Using the empirical weight times n, which is our objective, get the whole number multiple to get the, and set it equal to the given mole weight. So we now have the empirical weight 45 atomic mass units times n to equal 90. And so n now is 90 over 45, or 2. With this, we can multiply the 2 through the empirical formula, and we wind up with C2H2O4 molecular formula.